The positive and negative charges, when combined together, cancel the effect of each other in the same manner as the positive and negative numbers in the maths. For example, if two bodies of charges plus 5 coulomb and minus 3 coulomb separately are brought in contact, then there will be plus 2 coulomb on the combined body. Okay, and next, if a charged body, suppose A, if charged body A attracts another body B, then it is not necessary that body B is oppositely charged. It may be an uncharged body also. So we can say attraction is not the real test of the body being charged. But if body A is repelling body B, then certainly body B is likely charged. Okay, so repulsion can be taken as the real test of a body, whether it is charged or uncharged. So the instruments used to test the charge on a body, the nature of the charge, relative amounts of charge on the bodies, so that is called electroscope. Gold leaf electroscope is the most commonly used one in practice. For electrification of body, only electrons are responsible. There will be only transfer of electrons and not the protons. Okay, so if suppose if you are taking body A and body B, they should be of different materials. Okay, then only the transfer of electrons will be taking place. And let us learn one more thing. And if we are rubbing these two bodies together and there is a transfer of charge, that is that there is a transfer of electrons. So let us suppose assume if body A is losing electrons and body B is gaining electrons. Okay, if body A is losing electrons and body B is gaining electrons, that means electrons has some mass. So on losing electrons, body A has lost some of its mass and body B would have gained some of its mass. So its mass is decreasing and its mass is increasing. So we should understand that point. Now let us see what is electrostatic induction. The process in which the charged body induces charge in an uncharged conductor placed near it without touching the conductor, that is called as charging by electrostatic induction. So let us see this example. So in this case, there is a body A with some positive charge and body B, that is the stand which has shown, that is an uncharged body and we want to charge it by induction. Okay, and if we are bringing that positively charged plate near to the body, uncharged body, then we can see the negative charges. In the first figure, negative charges are being coming to this left side. Why? Because the positive charges in the body A will attract the uncharged body. So the negative charges would come on the side, that is the side of B. So if the negative charges are accumulating on B, then the positive charges would go and accumulate on C. So that is first case. Okay, in the second case, what we are trying to do, we are keeping our hand on the side of positive charge so that it is the positive charges flowing into our hand, or we can say it is earthed. So if we are earthing the side C, then all the positive charges would flow into the earth. Okay, then in that rod there will be only negative charges, so those negative charges are distributed equally in the rod. So that is what is shown in the C, and this is an example of process of electrostatic induction. SI unit of electric charge is coulomb, and we know electric current is equals to charge by time. So I can say if a conductor carries 1 ampere of current for 1 second, then the charge flows through that conductor will be 1 coulomb. So 1 electron has 1.6 into 10 power minus 19 coulomb of negative charge. So that is the value of charge of 1 electron. Okay, it is a coulomb of negative charge. So for 1 electron, it is this thing. And now we have to learn about the 3 important properties of electric charges: quantization, conservation, and invariance. So in Millikan's oil drop experiment and many other experiments have shown that in nature the charges are found to be made up of integral multiples of smallest amount of charges. Okay, the smallest amount of charge is 1.6 into 10 power minus 19 coulomb, and that can be denoted by E. Okay, that is the smallest charge ever known, and it is also the charge of electrons. All the existing charges found in the nature are found to be n into E. So n can be any integer. It is E, 2E, 3E, or minus E, minus 2E, minus 3E. So we can say charge Q on the body must be given by n into E. Okay, that n is nothing but 1, 2, 3 or minus 1, 2, 3, whatever. So from this we can say electric charge cannot be divided indefinitely. So this property of charge is called as quantization of charge. Next one is conservation of charge. So again, in experiments, it shows that total amount of charge in an isolated system, it is always constant, or we can say charges are neither created nor destroyed. So that is nothing but conservation of electric charge. Next, invariance property, it states the value of charge, it will not be varying with the change in velocity. So if there is a static charge, that is an immobile charge, it is having charge qs and it is moving with velocity, some velocity, then in the moving state also it will have the same charge when it was at the static state. So that is called as invariance property of the charge. So now let us see about Coulomb's law. So if there are two stationary point charges q1 and q2, they repel or attract each other with a force with which that is directly proportional to the product of charges, and it is inversely proportional to the square of distance between them. So this is called as Coulomb's law, and this force will be along the line joining the two charges. Okay, so F is equals to K into Q1 Q2 by R square, and the value of K is found to be 9 into 10 power 9 Newton meter square per Coulomb square, and K is also equals to 1 by 4 pi epsilon naught. Okay, that is equals to 9 into 10 power 9 Newton meter square per Coulomb square, where the value of epsilon naught is found to be 8.85 into 10 power minus 12 Coulomb square by Newton meter square. So we have seen the formula for force, that is 1 by 4 pi epsilon naught Q1 Q2 by R square. But in general, you should know this is the formula for force, that is 1 by 4 pi epsilon Q1 Q2 by R square. Why we are writing like this? Because in general, the charges are not always present on the air or vacuum. It can be also in some other medium. So if it is placed in some other medium, then the value of dielectric constant will be changing. Okay, if we take air or vacuum, then the value of dielectric constant, that is K, this dielectric constant K is also called as relative permittivity. Okay, this will be equals to 1. This is for air or vacuum, but for some other medium, this K value is not equals to 1. So if it is air, then we can say instead of epsilon naught, if we are substituting epsilon naught into K, and that K will be equals to 1. So this is the formula suited for air or vacuum. But in other cases, if it is at some medium, then the value of force is equals to 1 by 4 pi epsilon naught K Q1 Q2 by R square. And I have actually didn't tell about the names of epsilon naught. So epsilon naught is nothing but permittivity of the medium. Okay, epsilon naught is the permittivity of the medium, and epsilon naught, so that is epsilon naught is the permittivity of free space. Okay, K is dielectric constant or relative permittivity. Yes, now I have mentioned. So this is absolute permittivity, and this is permittivity of free space, and this is dielectric constant or relative permittivity. So with that, the formula for force changes. That is epsilon naught into K. Instead of epsilon, there is epsilon naught into K. So depending upon the conditions, if K is given, then we have to use this formula. Now let us see the properties of Coulomb's law. Coulomb's law is based on experimental results. It is not established theoretically. It cannot be established theoretically. It is only holding good for point charges. This law is applicable for charges at rest. Okay, because charges at rest produce only electric field. Please remember this point. Charges at rest only produces electric field, but the charges in motion, it produces both electric field and magnetic field. Okay, so Coulomb's law is not for charges in motion, it is only for charges in the rest. Okay, the third point, it is obeying the Newton's third law. Okay, because it forms a action reaction pair, so it obeys Newton's third law. It is a central force, that means it acts along the line joining the centers of the charges. It acts along the line joining the two charges, that is why it is called a central force. And the force between the two charges is not changed by the presence of other charges. Okay, that we have to understand. Now we have to see another thing. So please see this. If suppose this is the force in the air or vacuum, that is 1 by 4 pi epsilon naught q1 q2 by r square, and this is the force which is in some other medium, that is 1 by 4 pi epsilon naught k into q1 q2 by r square. Okay, so this k is representing dielectric constant. Now if this has some value, that is 25, then what will be the value of this f dash? This will be 25 by k. If that k is again 5, that is 25 by 5, that is 5 only. So f dash will be only 5. So what I can say, the force is maximum, that is 25 when it was in air or vacuum, and if we are placing it in some other medium, then it is reduced by when we are dividing it with the dielectric constant, then it is reduces to that amount. So the value of force is maximum at air or vacuum, and when we are inserting some dielectric, when we are keeping the charges in some other medium, that is with some dielectric constant, the value of force reduces. So that is what I have shown. Force is maximum in air or vacuum. If suppose it is F naught in the air, then in the medium of dielectric constant K, it will be F naught by K. That is what I have shown. It obeys inverse square law. Okay, just like gravitational force, the force is inversely proportional to the square of distance between the charges. So it is inverse square law. Now let us see the concept of electric field. The space around the electric charge Q, in which another charge Q naught can experience a force of attraction or repulsion, that is called as electric field of charge Q. Okay, now this electric field, this is nothing but F by Q naught. Let me explain that. So please see, there are two charges Q and Q naught, as we have already seen. The force of attraction or repulsion between them is given by Q naught by R square. Okay, but here I am interested in finding electric field because of the charge Q. Okay, so electric field because of the charge Q, that is equals to KQ by R square. We should not write Q naught because we are finding the electric field of Q. I am using Q here. E equals to KQ by R square. What does it mean? If I am bringing this Q naught here, then F by Q naught is equals to E. That is what I have written here. Okay, E equals to F by Q naught. That is nothing but KQ by R square, which is the electric field of the Q. Okay, both Coulomb's force and also the electric field, both are vector quantities, but charge is a scalar quantity.